Welcome all of you. In the last class, we started discussing about spin echoes. I told you what is a spin echo. It is obtained by the application of two pulses with a delay. It could be 90 tau 180, 90 tau 90 tau. And the two delays should be exactly equal. Afterwards, you are going to get an echo. I explained to you how the spin echo works. Then what is going to happen is the spin vectors once you apply a first 90 pulse, bring it to x-axis or y-axis, they will start dephasing with the time. And then after some time, what will happen when they are dephasing? There will be fast moving and slow moving components. And they with the time t, they will start moving. And after certain delay, you apply a 180 pulse. Then what will happen? The spin vectors get interchanged. Fast moving becomes slow, slow moving becomes fast. So they get interchanged. As a consequence, after some time, all the spin vectors will assemble at the same place, in the same axis. Is exactly I gave you an analogy of runners. Several runners will be asked to run for a distance. They will be running at different speeds. After certain time, you ask them to stop where they are. Some would have moved long distance, some would have moved short distance. Whatever the distance they have moved, they are all at different distances. Like spin vectors dephase at different frequencies, at different phases. And immediately ask them to turn back and run back at the same speed. They will all assemble at the same place. This is exact analogy for a spin echo. That's what happens for the spin echo case. And I explained to you, if taking an example of homonuclear two spins and multiple spins, I showed that whatever may be the offset chemical shift difference between the vectors, doing a spin echo, the chemical shifts get completely refocused. As a consequence, chemical shifts will not evolve. There won't be any chemical shift at all. It appears as if there is no chemical shift. They are all refocused. This is what we understood. Now the question comes is, what happens? Why only chemical shift? What happened to the J coupling? That is the thing which we need to understand. Let us consider what happened to the J coupling. Of course, in AX coupled there should be J also, but I took an example of a J being 0, so that only chemical shift I wanted to consider. Now I will consider an example with J being present. An example of two spins A and X. This is what it is, A and X two spin coupled. And then we have doublet for A. Why the doublet comes? We have been discussing quite a bit, because of the spin states alpha and beta of the spin X. Similarly, X will also have the doublet. We will consider what happens to the doublet. Let us say I am going to apply a 190 pulse and bring the magnetization to the X axis. I will consider, let us say, spin A or X, whatever it is. Then it will have doublet. I am considering spin A for the position when it is coupled to spin X, alpha and beta components. Then we will have two vectors here, one corresponding to alpha orientation of X, other corresponding to beta orientation of X. So we have two vectors. And with time delay, what happens? These alpha and beta vectors of A start moving in either direction. So one is a fast moving vector, other is slow moving vector with respect to this X axis. One moves toward this side, one moves toward this side. Fine. Now you apply a 180 pulse. What is going to happen? I said everything gets reversed. Okay, you apply a reverse 180 pulse. Now beta, alpha is here, alpha went there and beta came back here. In the chemical shift case, what happened? They continue to move in the opposite direction and then refocus along X axis. That's what I said. But now there is a J coupling. What is the meaning of that? That means after again certain delay, the question comes, will they start moving in the opposite direction? Will they refocus? Or will they move in the different direction? Will they continue to move in the same direction or in the opposite direction? Will they refocus or not? Is the question. We will answer this question now. Remember, when we have the vectors will they refocus or not is the question for which, remember, 180 pulse also inverts the relative orientation of J coupled partner. You are considering the doublet, two vectors of the A spin which is coupled to X. But 180 pulse also inverts the orientation of X partner, that is to alpha and beta of X. As a consequence, what happened? The doublet component of A, which is coupled to X alpha, will now be coupled to X beta. Remember, doublet A will have two components, A alpha, A beta. That comes, A alpha comes because of X alpha, A beta comes because of X beta orientation, but they get reversed now. So X alpha will now be coupled to X beta and vice versa. Now the alpha and beta components are interchanged. That's what I said, because of 180 pulse also acts on X spin. What is happening now? The faster moving components move slower and vice versa. Then instead of refocusing, they continue to move in the opposite direction, in the same direction. They will not dephase. They will continue to dephase. Not they will not refocus. They continue to dephase. This is what is happening. They won't refocus now. Earlier, what happened in the case of only chemical shift? They after 180 pulse they started moving backwards like this, and then refocus along the x-axis. But now, because of J coupling, they started moving in the opposite direction like this. So fast and slow moving component exchanged. They started moving in the opposite direction. So there is no question of dephasing. In fact, it continues for no question of refocusing. Continuously dephasing goes on. So that means J splitting in the homonuclear case are not refocused in spin echo. Remember, homonuclear spin echo refocus only chemical shifts and not J couplings. Please remember, homonuclear spin refocus only chemical shifts and not J couplings. Okay, this is for the homonuclear case. You may ask me a question, what happens if I consider the heteronuclear spin? Like not homonuclear, like two protons. Instead of that, I will consider proton and carbon, heteronuclear spin. How the J evolution takes place under spin echo. Now we can think of several possibilities. For the J coupled heteronuclei, what we can do is we can apply 180 pulse only on the spin A. That is possible because heteronuclear are at different resonating frequencies, several megahertz apart. As a consequence, we can separately, individually apply RF pulse both on spin A, only on spin A, only on spin X, or both on spin A and X. Simultaneously we can apply. All the three possibilities exist. Whereas in the case of the homonuclear, if you apply a 180 pulse on A, simultaneously X pulse which is coupled to it also gets reversed because it is a homonuclear spin. But here I can separately apply pulse, 180 pulse, either only on proton, only on carbon, or both of them. Let us see when the 180 pulse is applied on either A or X only, what will happen to the this thing. So how the vectors will start moving. What will happen is, please remember, now I am applying the 180 pulse only on A or X. Only that spin will experience 180 pulse. It will other heteronuclear spin will not experience because they are megahertz apart, and it is not going to be touched at all. It is not getting affected at all. As a consequence, only particular spin on which you apply 180 pulse experience this 180 pulse, and the effect is seen only on that. So in such a case, what will happen? Similar to chemical shift, J coupling will refocus. What happened after the 180 pulse is applied only on that, because in this case coupled spin is not touched. Only when coupled spin is touched, I said alpha and beta components, if H alpha, for example A alpha coupled to H alpha or C alpha for the heteronuclear spin, will get to beta spin. So that get interchanged, alpha and beta spin states. That will not happen now. So similarly, like chemical shift, they continue to move like this and then refocus. What does it mean? If you apply 180 pulse on only any one of the spins, J coupling will refocus. What happened in the case of homonuclear? J was not refocusing at all. But in the case of heteronuclei, whether you apply 180 pulse only on A or only on X does not matter, J will refocus. Okay. This is what happens. In fact, we always say 180 pulse on a heteronuclear spin generally results in decoupling. This is the phenomena. What do you mean by that? J couplings will not evolve. See, for example, this internuclear vector comes along y axis, because of J plus half and minus half, they will start moving in the opposite directions, and after the 180 pulse what will happen? They will again continue to move in the same direction. They get interchanged, but then continue to move. Instead of J moving like plus half moving like this, it start continuing to move in the same direction. Only this positions get interchanged, but the direction of motion is continuing to be same direction. As a consequence, what happens? They refocus along same axis. It is nothing but telling decoupling. So remember, we always say you apply a 180 pulse at the middle of the evolution period in one of the spins, A or X spin, in a heteronuclear system, then you will have J coupling. Refocus is nothing but decoupling. That is the concept. Now you may ask me a question. So far we was considering only application of 180 pulse on A or X. This phenomena happens, J will refocus. What happens if I apply 180 pulse simultaneously on both heteronuclear spins? It is possible. Then what will happen? It is like applying to homonuclear spin. If you apply A 180 on A spin, X spin states gets interchanged also. As a consequence, so A which was alpha state will experience beta, similarly gets reverse, vice versa. Exactly analogous to homonuclear situation. When you apply 180 pulse simultaneously on both heteronuclear spin, then vectors will start dephasing. There is no question of refocusing at all. Vectors will not refocus. You understand? Please remember the concept. In the homonuclear spin echo, chemical shifts are refocused but not J coupling. In the heteronuclear spin echo, if 180 pulse is applied on any one of the heteronuclei, A or X spin, then what will happen? J will refocus. Whereas if you apply 180 pulse simultaneously in both A and X spins or both the heteronuclear spin, J will not refocus. This is important concept you must remember. So heteronuclear spin echo is like this. This is a situation where I am going to apply 180 pulse both on I spin and S spin. I and S are heteronuclear spin. Usually I is considered as proton, S as a heteronuclear spin, some other spin. Offsets are refocused, J coupling will evolve, they will not refocus. That is what I said. 180 pulse simultaneously on both, no question of refocusing of J coupling. So only but chemical shifts get refocused. That like 180 pulse, like in the homonuclear case. Like homonuclear system, chemical shift refocus, but J coupling will evolve. What happens if you apply 180 only on I? Just now we discussed, only I spin offset is refocused, but J coupling is also refocused. S spin nothing will happen. S spin will keep chemical shift keep evolving. Now apply 180 only on S spin, not on I spin. What is going to happen? Extend the logic. Now S spin offset is refocused and J coupling is also refocused. But I spin offset, I spin chemical shift, nothing happens. These are the three different spin echo experiments you can do when you have heteronuclear spins involved. Alright. With this idea, we understood now what will happen to spin echo case. Spin echo is a summary is just 90 tau 180 tau sequence. Depending upon whether you are applying a homonuclear spin or heteronuclear spin. If it is a homonuclear spin, chemical shift will refocus, J coupling will not refocus. If it is a heteronuclear case, if 180 pulse is applied on one of the spins, J will refocus. Whereas if heteronuclear spins are applied simultaneously like this, what is going to happen? J will continue to evolve if I apply simultaneously on both. That is it. Okay, now we will see some J modulation of spin echo. This is something important concept you should know. What is the meaning of J modulated spin echo? Let us consider the 13C spin echo sequence under decoupling. What is a spin echo sequence? It is nothing but this one. 90 TD, 180 TD. This is a delay for echo. Both are identical. 180 pulse you can apply Y or X, doesn't matter. And then what we do is, after this immediately we start collecting the signal by decoupling proton. We need to do the decoupling. Because we need the carbon 13, as I told you, always recorded with the broadband decoupling, so that you get individual resonances for each chemically inequivalent carbons. So we have to do the decoupling. Fine. In the first TD, what will happen? Coupling between carbon and proton. Here I am taking carbon and proton, they evolve. But during the second TD, what is happening? I am applying the RF pulse, they are decoupled. But chemical shifts are refocused during both the time, that we have already understood. Chemical shifts get refocused, but J coupling gets decoupled in the second delay. Okay, this is what is the spin echo we have to do and the decoupling. If we have to decouple this thing. But how does these different carbons evolve in the spin echo sequence? Now I am considering the heteronuclear spin echo because I am looking at carbon coupled to CH, CH2, CH3 and quaternary, all the four. How these vectors evolve in the spin echo sequence? We will try to understand that. And of course, I am considering one band coupling. Forget about long range couplings, we are not bothered. The evolution of magnetization vectors after the 90-degree pulse, we can understand it in a simpler possible way. There is an equation which I have not discussed in the previous courses I have discussed. After applying a pulse, bring the magnetization to x axis or y axis and give some time delayed TD, the spin vectors start dephasing. They start moving in different faster and slow moving components will be there. And depending upon the strength of the coupling, they start moving. How fast, how much it has rotated, how much they have moved in the xy plane is given by an angle theta. And theta is given by pi into time delay into J coupling is the value. If you know this J coupling, if you know how much time you have delayed, the delay you have given, then I can tell you how much the spin vectors have moved in the xy plane. Very easy to calculate. All you need to know is time delay and J coupling. And I know this is a constant. I know angle by which these vectors have moved. Okay, that's correct. Now, next is, but remember one thing, since we are worried about the J coupling, quaternary carbons always stationary. There is no J coupling, there is no fast moving, slow moving components. They remain stationary. They will be always along one axis. So, if you detect that, you will always get a positive signal. There is no question about it. You bring the magnetization to x axis from the z axis, put a receiver here, you always get signal for quaternary, positive signal. Fine. What happened to other carbons? We are not worried only about quaternary carbons. What about other carbons? And let us consider one by one. First we consider only CH carbon, carbon coupled to proton. What is the multiplicity pattern? It is a 2 spin coupled, 2 spin of carbon will be a doublet. We are not worried about proton, we are looking at carbon. Carbon will be a doublet. Alright. Now what we will do is after 90 degree pulse, the doublet components alpha and beta of carbon start evolving under JCH and for the interval TD which is given in the spin-echo sequence. What is JCH? We can always know, we know the JCH. This is the diagrammatically what happens. Magnetization initially at thermal equilibrium, it is at thermal equilibrium, apply 90 pulse and bring it to x axis. They start rotating the x and alpha and beta component in opposite direction, fast moving and slow moving components. But remember, exactly after 90 pulse, 45 degree, 180 degree, what happens? We can calculate using that equation. Theta is equal to pi into TD into JCH, that we know that. We can calculate. Now for different values of J, how much it moves, we will find out. For example, for TD exactly to 1 over 4J. Whatever the J value, I don't care. How much it has moved? Put TD is equal to 1 over 4J. This J and J cancel out. It is 1 over 4 of pi, it is 45 degree. What will happen is the spin vectors, both alpha and beta components would have rotated by 45 degrees. That's fine. So, this is how it is. At exactly 1 over 4J, x and y components have moved by 45 degrees. In the xy plane I am talking. Okay. It is I am showing only the 2-dimensional graph, but it is from z axis it brought to xy plane. You have to see in the, imagine in a 3-dimensional plane I am in the xy plane I am talking. They have moved by 45 degree. From x axis it was there, started moving like this. Spin vectors would have rotated by 45 degree. That is what we calculated. Fine. We will go further. Calculate what happens if it is 1 over 2JCH. That is, again put the value TD is equal to 1 over 2JCH, then it is become 90 degree. What would have happened? The magnetization would have come along x axis and now they start moving in the xy plane by 90 degree. Both of them would have moved on 90 degree. From x it would have come to y, plus 1 minus y components would be there. So, they will be opposite in phase. They will be anti-phase magnetization. See, if the doublet vectors both in the same phase like this, they are in phase doublet. If one is positive, other is negative like this, it is called anti-phase doublet. So, now after exactly 1 over 2 JCH, the alpha and beta components would have become anti-phase. They would have acquired anti-phase character. Okay, exactly phase difference of 180 degree. One is here. Y along y axis, because in the xy plane you remember 90 degree from x axis they would have moved and z is along this axis. So, they would have one component would have moved to plus y, other would have moved to minus y. So, that is what I am showing you here, and it would have acquired a phase difference of 180 degree. Then if you measure the intensity, have a receiver here, it is 0. Whereas the quaternary it was here and you measured from here, it was full intensity. But now CH intensity at exactly equal to 1 over 2j, because this vector alpha and beta vectors are opposite of in phase by 90, each of them are antiphase in character, there is a 180 degree phase difference, intensity is 0 because positive negative component of the vector gets nullified. There won't be any signal, you will not get a signal. Fine. Now after the time delay you apply a pulse, pi pulse, what will happen? We are given the delay after exact 1 over 2j, it would have become antiphase. Now we apply a pi pulse. What is the duty of the pi pulse? I have not discussed in this course, but in the previous course I have discussed. Pi pulse always invert the signal. From plus z axis it will bring to minus z axis. In other words, what is going to happen is it will completely reverses from alpha and beta component from plus z to minus z to plus z, and inverts the magnetization. Simultaneously you start doing the proton decoupling. This is what happens. Alpha and beta components you can start resolving into vectors, and let us say after 90 degree they get interchanged, invert 180 pulse invert the magnetization, and from here to here it became like this. Now resolve into two components, this sector, vectors in the opposite direction gets nullified, this gets added up. So there is a magnetization along this axis. Where is that magnetization now? It is in the minus x axis. What happened now? In the case of CH vector at exactly equal to 1 over 2j, you apply a 180 pulse and you see magnetization is along minus x axis. Both the opposing components are cancelling out. The vector addition cancel this one, whereas this one gets added up. Alright. That means you are going to get a singlet. That is fine. So each doublet vector, now at for theta is equal to 1 over j, we have 180 degree, each doublet vector will rotate through 1/2 like this. From here it will go to 1/2 like this, other one comes like this, and then they meet again at minus x. That is what it means. Of course, the components along this axis is nullified, only this component we are detecting. Alright. In effect, what do you understand from that? In the homonuclear spin echo we discussed this. Vectors start defacing and again they come back into the same axis, both the vectors. We called it as refocusing. It means chemical shift, there is a refocusing, but the signal is along minus x axis. Instead of detecting in the plus axis, signal is in the opposite direction, minus x. What does it mean? It means if you detect the signal like this, you have a receiver here, signal is along this axis, you get a negative signal. Same signal with a negative phase. Negative signal means negative phase. Quaternary was here only and it is positive, CH is negative. That is what happens. So intensity of CH you can also calculate. I took only example of 2 or 3 time delay, like half j, 1 over 2j like that. But instead what will happen as a function of delay? Keep on varying the delay and calculate it. At exactly equal to 1 over 2j signal is 0. That is what we saw. At exactly 1 over j, it will come back and it is a negative intensity. That is what we saw. At 1 over j, the vector component start moving and then reassemble, refocus in the negative x axis. So you are going to get negative signal for CH. So CH carbon, you get a singlet, there is a chemical shift refocusing, but also negative intensity, a singlet to negative intensity. And how does the intensity vary? It depends upon the cosine of the angle, cosine of the delay, and it is 0 for TD values equal to multiples of 1 over 2j and maximum for 1 over 2j. That is like what you saw in this graph. It is 0 for 1 over 2j or multiples of that. It is always like this for multiples of 1 over j. So JCHS generally are not identical. You may ask me a question. Different carbon with the proton one bond coupling could be different. It need not be same. Different molecule, one may have 140, one may have 150 hertz, other may have 200 hertz, 170 like that. We always assume approximate value of 150 hertz and then start the work. What happened to a CH2 carbon? Something interesting. CH2 carbon is a triplet. Central component will not precise. It will always gets aligned along x axis. Now what will happen for a T day? Again same, apply 90 pulse, bring the magnetization to z axis, x axis and give a delay. what will happen exactly at 1 over 2j, this will come back. Earlier they were anti-phase like this, but now they are going to minus x axis. Why? Because remember, in the j coupling here is like this for one doublet, whereas here in the triplet this itself is j, not half like here. Here if you measure this j, you have half of the j, one component is here, half the j, this is half j, whereas here 1 j. That means if you have a triplet, one of the component with respect to the central component itself is the j value. It is almost twice of j coupling between this one doublet, we will say. For the doublet it is almost half of it compared to triplet. As a consequence, for 1 over 2j, instead of CH proton, where it's have an antiphase with along y axis, they come back and refocus along this. Okay, we will now give another time delay after the 180 pulse. Continue, see what is going to happen. They come back and all the 3 components 1 to 1 we get aligned here, and we are collecting the signal here. What is that we are going to get? CH2 carbon has a signal intensity as a function of TD. When you consider the situation of a triplet, it is like this. At exactly 1 over 2j, it is 0 intensity. You may be surprised. Why it is 0 intensity? Previous CH case, they were antiphase along y axis, it was 0. But now why it is 0? We'll go back and see here. Both the components of the vector doublet here and a center component is here. Again, vector addition at 1 over 2j is 0. So as a consequence, you can see at 1 over 2j, its intensity is 0. At 1 over j, all the 3 vectors come back to the x axis. They reassemble there. They refocus. As a consequence, it is a positive intensity. So CH2 will be a positive intensity. For CH2 carbon also, you can monitor the change in the intensity like that. You may ask me a question, what happened to CH3 carbon? CH3 carbon, remember, has 4 vectors. From the center, we have 1 3 3 1. But what is going to happen is like this. Okay. So now let us see, CH3 carbon has 4 vectors, 2 fast moving and 2 slow moving. After the TD delay, they will be like this. 2 fast moving and 2 slow moving will be like this. After apply a pi pulse, then again reverse it. Pi pulse inverts the magnetization, you invert it. Now depending upon which axis you are going to apply, I showed you already. You can apply along this axis, rotate like this. If you apply along this axis, you can rotate like this along y axis. It is rotated. Again resolve into 2 components. The components along this axis gets nullified because of vector addition, whereas this one gets added up. Okay. After some time delay, exactly when T day is equal to 1 over j, then what will happen? They will refocus and you get a singlet. What is happening now? Your receiver is here. Signal you are going to get is negative again, singlet with a negative intensity. That is what happened. The behavior of CH3 is similar to CH. The intensity is maximum at 1 over 2j and negative maximum at 1 over j. Now CH3 carbon variation, if you see it, exactly at 1 over 2j, it is 0. All the 3 carbons CH, CH2, CH3 at exactly 1 over 2j signal intensity is 0. But at 1 over j, CH3 and CH are negative, CH2 is positive. That is important, you should remember. So I am showing this in a table like this. You have different time delay. Delay when it is equal to 1 over 2j CH. For a quaternary carbon, it will never persist, always positive. CH carbons at 1 over 2j, all CH, CH2 and CH3 are 0. Whereas at 1 over j CH, CH is negative, CH2 is positive, CH3 is negative. We can calculate that. The signal intensity as a function of J is modulation is like this. As a function of J modulation, if we keep on varying the TD activity which correspond to 1 over T or 1 over 2J like that, when it is exactly at 1 over 2J which correspond to 90 degree, all the carbons will have 0 intensity. CH3 is, CH2 is positive, CH3 and CH are negative at 1 over J. You see, at 1 over J it keeps going, and that is how it is. And only quaternary carbon is seen. Important thing you remember, quaternary carbon is unaffected. As a consequence, 1 over 2j, quaternary is always positive. That is always seen. Only other 3 carbons are 0. So the delay changes 1 over delay which depends upon 1 over JCH makes CH and CH3 carbons have one particular sign, CH2 and quaternary carbons of opposite sign. Whether you make this positive or that positive is your convention. Normally, conventionally what is done is these two are always made positive, phase corrected, and these two are made negative. You can do the way you want, you can reverse it also, but convention followed is this one. So J coupling, although it is different, assume to be 150 hertz and do this, and this is what happens. Look at it, a simple example, hypothetical example of a molecule like this. CH2, CH3 are and quaternary are positive, CH3 and CH are negative here. This is called attached proton test. By doing this spin echo experiment with J modulation at setting a delay which is equal to 1 over JCH, you can find out depending upon the sign of the signal whether it is positive or negative. You can say whether it is CH or CH3, whether it is quaternary or CH2. That is possible. This is a realistic example of a molecule. See, for this, these 3 are positive, correspond to CH2, and this is quaternary is positive. These are all CH3 and CHs. And this is an example of a molecule triterpene. You see, when delay is equal to 1 over 2j, what do you expect? I showed you 1 over 2j, all the 3 carbons are 0. All the CH, CH2, CH3, but quaternary is not 0. So if you set the delay equal to 1 over 2j in the attached proton test, only carbons which has not attached to any protons you are going to see, including CdCl3 solvent. Whereas at J is equal to 1 over J, you can see that this is CH2s are positive, CH and CH3s are negative, and this is a conventional. Compare these two. You can identify what are the quaternary carbons, you can identify what are the CH2 carbons and what are the CH3 carbons. But only thing is how do you distinguish between CH and CH3 is a bit problematic, that we have to see later. So this is an example of an APT spectrum of menthol. Again, we have a lot of CH2s and CH3s here, and all the 3 CH2s are here, and these are CH and CH3s. So basically what J modulation I wanted to cover in this example, in this class is, it is called an attached proton test. We discussed about the heteronuclear spin echo, and I said when you apply only 180 pulse on only one of them, J will not refocus, only chemical sheet of that will refocus, whereas if apply 180 pulse on both, then J will refocus. So all those things we discussed. Okay. We understood everything what is happening for the homonuclear case and heteronuclear case. And then in the J modulation I said when you use a spin echo sequence with proton decoupling, depending upon the delay you is going to use TD in the spin echo 90 tau 180 tau sequence. Depending upon the delay, when delay is equal to 1 over 2j, all the CH3 carbons are signal intensity 0, only quaternary will be seen. Whereas when it is exactly equal to 1 over j, then CH2 will be positive, CH and CH3 are negative, and quaternary is also positive. This way we can do the identification of different carbons attached to a different number of protons. This is called attached proton test. The basic thing for this is to understand spin echo. If you know spin echo, homonuclear, internuclear case, how it happens, you can do this modulation, J modulation experiment and identify different carbons. Thank you very much. We will continue further in the next class. Thank you.